to welcome Jim Adams to our school to give a presentation. The content is going to be on the future of space exploration. Now, Jim has recently retired from NASA. He has over 35 years of aerospace experience. He has directed or been involved in over 30 spaceflight missions to explore the Earth, the Sun, and most of our solar system. He last served as NASA's Deputy Chief Technologist, advising the Administrator on NASA's technology portfolio and advocating the use of new technology throughout ages, influencing $6 billion annually. Mr. Adams has also served as NASA's Deputy Director of the Planetary Science Division. He was responsible for a $1.5 billion annual budget for many missions, including the Mars Science Laboratory, Pluto-New Horizons, Dawn to Ceres and Vesta, and Messenger to Mercury. He has served on the National Science and Technology Council's Strategic Computing Initiative, helping to assure that the U.S. space high-performance computing needs will be met by our U.S. investments in computing technology and infrastructure. He also made a comprehensive assessment of the U.S.'s plutonium-238 production capability and infrastructure and many other independent reviews of agency capabilities. He has been awarded 3 medals for outstanding service and leadership by the agency, holds a Bachelor of Science degree in physics and a Master of Science degree in electrical engineering. Please all welcome Jim.
Doesn't work. So, microphone doesn't work, and I have a funny accent, so please forgive me. Do not tell the police I took my mask off. Yes, so that was a great introduction. I couldn't have written it better myself, which I did. But I wrote it 5 years ago, so now it's 40 years instead of 35. But I thought maybe what we do is just go ahead and get started with derive the ideal rocket equation. I'm joking. I was born in 1957, the same year that Sputnik was launched. As you heard, I have a BS in physics and a master's in electrical engineering, 40 years of experience, 30 successful missions. I retired in 2016, and now I'm a consultant and an advisor, and I'm an advocate for STEM education. And that's actually why I'm here in South Africa for this month, is to promote STEM education among learners, grades R through 11. So, though I didn't just come from SANSA, where we were talking about ways that we can promote space exploration in and around your country. This is my 15th trip to South Africa since 2013, and we'll talk about why that is in a few minutes. I did get an early start. That's my cousin and my sister. They're designing our first rocket. But years later, I was actually sitting next to the administrator of NASA, that's General Charles Bolden in the foreground. 3 shuttle flights, and NASA administrator was a remarkable man. We were in the midst of launching the Grail mission to the moon. No. We'll get to that. There we go. So this is a Delta II rocket taking off. And what you're going to see in rising out of the cloud of smoke, the thing that is because there's a main engine in the first stage that's fed by liquid oxygen and kerosene. And then there's 9 solid rocket motors that are strapped on the outside. This is pushing a pair of spacecraft to the moon. And what you'll see is the first 6 will burn for a minute, and then there'll be 3 that will light up and it'll burn. And then when it disappears into the clouds, I'll just let it turn on. No, go away, frog. There we go. 2, 1, ignition. And that's mostly steam that you see coming off the pad. So, and the interesting thing for me, after seeing dozens of these, is it never gets old. I still love watching the video. It's still extremely powerful, and if you ever get the chance, no matter what size the rocket is, you should go see one, because it's inspiring. So the vehicle just went transonic. Not that you can tell by looking at it. So it just hit max Q, which is the maximum air pressure. So it's now 13 miles downrange. Let the solid rocket mode, the first 6 burn out. They kick them away. There they go. And then they light the next 3. Now the rocket weighs half of what it did 90 seconds ago. That's how fast the fuel is being ejected. I'm going to stop it there, and I'm going to tell the story. So, in order to keep the air-lit solid rocket motors from getting ignited by the first stage and the ground-lit solid rocket motors, at least on this rocket, we don't make this one anymore, but there were these enormous corks that would go into them. They were about this tall and maybe a meter diameter, and push them up inside the cone of the solid rocket motor, and then when it would ignite, the pressure would push the cone out. Different mission. We scrubbed a launch one night because the winds were such that we were concerned that the corks would end up landing back on the launch pad instead of downrange. And so we scrubbed the launch, which was a big deal, and then it went just perfectly the next night. Winds were perfectly quiescent, and we had a fantastic launch. That evening, one of the technicians was going home down the back road, inland about a mile, and there, right in the middle of the road, was one of these corks. So our weather prediction and simulation didn't happen so well. When you launch a rocket, you have to stand back about 5 miles. So we stood everywhere. This is a different rocket that we're launching to the moon. You've already seen the punchline of this one. Everybody was safe on this launch, except for the frog didn't get the message that he was supposed to get away. The payload got to the moon, but we never heard from the frog again. So this is me when I was a younger man. We were at the Jet Propulsion Lab flying through the coma of a comet. So, I was asked today to talk about the future of space exploration. And what you're going to find out as you talk with me is that I think it's very bright. There's lots of things going on. And so I didn't know how to put all this into a talk. So what I did was, like a NASA geek, I counted down. So we'll talk about the 5 missions that excite me most, the 4 data streams that people can tap into, 3 enterprises, 2 new initiatives, and what the one future is all about. Because it's my intention to convince you guys that the future is bright for space exploration, and we need bright minds going to work in that sector. So. I should also say, this is the first time I've given this talk, so I don't know how long it's going to go. It might be really short, but that's okay because I absolutely love to answer questions. So we'll talk about questions and answers when we get there. So the 5 missions that I'm very excited about is, of course, James Webb Space Telescope, a mission called Lucy, Dragonfly, Mars Sample Return, and then a pair of missions we're going to send to Venus, and I'll talk a little bit about that. So there's the mirror associated with the James Webb Space Telescope when it was being built at the Goddard Space Flight Center in Maryland. What's exciting about the James Webb is this comparison. It was just released last week. This was the WISE mission. And you can see how fuzzy this is. The same image, right? This is the Spitzer mission. Of course, there are different wavelengths, but you get the idea. You can see these 4 stars. And this just came off of the James Webb Space Telescope. It's stunning. And you can see where the stars are actually forming. You can see what's in the background. That's the cool thing about the telescope, is it's actually kind of a time machine, because these stars released their light billions of light years ago, and we're just picking it up today. Right? So that's the way the light looked millions of years ago. And when they get JWST tuned up, they expect to be able to look back to just before the dawn of the Big Bang, or just after the dawn of the Big Bang. So we'll have a sense of what the light looked like back then, which, by the way, is why it's an infrared telescope. Because as the universe has expanded over those, 30 billion years, the redshift of the light, the visible light, has now shifted into infrared, which is why the Space Telescope is an infrared telescope. So Lucy was launched last year, and it's going to go to a region of space that we've never been to before. I don't know if you know what a Lagrange point is. Should they know what a Lagrange point is? Lagrange points are spots of, it's actually a spot of instability, but people say it's a place where there's no gravity. It's actually not technically accurate. But because of the orbital dynamics, any 2-body system in our solar system has these 5 Lagrange points. The easiest one to understand is L1 between the Earth and the Sun. So Earth and Sun system has 5 Lagrange points. The L1 point is 1 million miles from the Earth towards the Sun. And that's a spot where the gravity from the Sun is balanced by the gravity pull from the Earth. The others get a little more complicated, but these L4 and L5 points, the Earth has them, the Earth Sun system has them as well, but Jupiter's Sun has these L4 and L5 points. We believe they've collected remnants of the earliest formation of our solar system. So it's like the samples are there and just go crap. And so Lucy is a mission that we launched last year that will head out and hit a number of targets in the L4 region, come swing back by Earth, and head on out to the L5. And we'll be able to compare the difference between the asteroids that were collected at L5 versus the asteroids that were collected at L4. And at the same time, we'll get a look back at Earth from the perspective of the asteroids, because we're going to be doing Earth flybys as we go. In fact, the first encounter is the Earth in October of this year. So it's on a big ellipse, and it's headed back towards the Earth to do a gravity assist, so that eventually it can head on out towards the L4 and L5 of the Jupiter system. One of the interesting things is, we say it's L4, Jupiter's L4 and L5, but in fact, the asteroids that we'll be visiting are closer to the Earth than they are to Jupiter. So it's kind of, it just kind of puts things into perspective for you. right now, on Titan, it's raining. Titan is the only planet in our solar system, aside from Earth, that we know of that has a hydrological cycle, evaporation, condensation, precipitation, and accumulation. Except, it's not raining water. It's raining methane, which is way cool. So right now in the southern hemisphere, these are lakes of methane. The southern hemisphere on Titan, I should say. These are lakes of methane that are filling up. And scientists tell me that if you do the physics associated with raindrop development, that has to do with surface tension and gravity and atmospheric pressure, that the raindrops themselves are as big as your fist. So what we're going to do, I think in large part because of the success of the Ingenuity helicopter on Mars, we're going to fly a quadcopter the size of a car that's nuclear powered into the atmosphere of Titan and explore these regions where it's raining raindrops as big as your fist. So that's planned to launch in 2027. So what are samples? I only have cartoons for some of these. Right now, the Perseverance rover is moving around the crater on Mars, and when it finds something that looks interesting, it puts a little bit of the sample that it's collected into a sample container, and it leaves it on the ground. Then it keeps on rolling, looking for more science to do. Someday, knock on wood, we will send the rover back, pick those up, cart it over to a Mars ascent vehicle, launch the ascent vehicle into orbit around Mars, release those samples in a container that the European Space Agency will come around, pick up, and bring back to Earth. When it gets to Earth, it's going to drop off the container, and it will descend through the atmosphere on a parachute. It's a major undertaking, and we don't have a date for it yet, but we know that we're going to do it. In fact, the Planetary Science Division, which is a survey of the science community conducted once every 10 years, was just released 2 weeks ago. And it says the most important mission for planetary science is this Mars sample. So the plan is, we'll go get it. We just don't know how yet. We don't have a Mars ascent vehicle yet. We don't know if we'll land the Mars ascent vehicle with no fuel on it, and we'll make the fuel with the water that we find on the surface of Mars. If you take hydrogen and oxygen and you disassociate them, you can make rocket fuel. So that would be a plan. It also complicates the mission. So we'll just have to see how it all plans out. But there'll be lots of international partnerships. And it would be really cool if we had some South Africans working on that. We recently awarded Da Vinci Plus, which is this descent probe, really lousy picture, by the way, to the surface of Venus and Veritas. This is a much better picture. Anyway, Venus is this planet, as most of you probably know, that is hot enough to melt lead on. The atmospheric pressure is something like 100 times the pressure on Earth. And so any probe that lands on the surface of Venus just doesn't last very long before it gets crushed like a volcano. But what's really important to us is the atmospheric chemistry on Venus. And the reason for that is because the situation on Venus in terms of runaway climate change, global warming, loss of greenhouse gases, or production of greenhouse gases, is an analog for what's happening on Earth. So we want to understand that chemistry. At the same time, there's a lot of questions around what does the surface of Venus actually look like? How young is it? Is it reforming annually, or is it old? And we just don't know the answer to that. So we will send a synthetic aperture radar to orbit Venus, and we'll send this descent probe to sample the atmosphere on the way down as it goes through the various layers, one of which is a layer of hydrochloric acid, gaseous hydrochloric acid. That's going to launch in 2028 and 2030. So, the 4 data streams that I'm excited about have to do with space weather, the Square Kilometer Array, the Atlas Telescope, and climate change. So, space weather. The sun is this amazing fiery ball, and it sends off these things called coronal mass ejections, pieces of the sun that get hurled off of the surface because of the entanglement of the magnetic fields. And they come streaming out into our solar system, and sometimes the Earth runs into them. The cool thing is that we're protected by the magnetic field that we have. We have this coherent magnetic field. It interacts with the coronal mass ejection. It often deflects the solar wind and these CMEs, they're called. And sometimes the particles get trapped by the magnetic field, and they come spiraling down towards the magnetic north and south poles. And when they do that, they interact with the upper atmosphere, and that's what makes the northern and southern lights, the aurora borealis. Beyond being pretty, it's also a huge laboratory for understanding plasma physics. So we want to understand that. In addition, this energy that comes into the Earth system affects things. And it affects things like, GPS signals. It affects things like communications to airplanes and vehicles. It affects undersea cables and pipelines, and especially power grids. In the United States, there was a power grid in the Northeast that was not robust enough to withstand the impact of a solar storm, and it went offline for a week. That's like load shedding. Only naturally. So we kind of want to understand the interaction between the Earth and the Sun. The other, I've had the privilege of visiting the Meerkat. Have any of you been up to the Meerkat? Oh, got 1 or 2 hands back there. Awesome. It's an amazing radio telescope that's going to produce enormous amounts of data. Actually, it already had started. And it's going to be part of a much bigger radio telescope called the Square Kilometer Array. The medium frequency, the mid-range frequency is housed here in South Africa, the Northern Cape, and the low frequency is in Australia. So it's a global initiative among scientists to understand our, not our solar system, but our universe from a radio telescope point of view. And I didn't put the picture in, but they turned it on, and one of the very first things they found was the first image of the region around the black hole by a radio telescope. So it's quite exciting. And if you think about the kinds of things that would be needed for that, actually it was visionary, because at the time that they started building it, the capability to process all of the data that these antennae would produce was, it just didn't exist. So not only did they have to build the antennas, but which I think they're up to 64 at the moment, 64 13-meter antennas. And then they do interferometry between all of them. And not only did they have to build the antenna array, but they also had to develop the computers to process the data that they would collect. So it's an amazing achievement in South Africa. Let's see. Oh, and the last. This is what brought me to South Africa the very first time in 2013. I was given the charge from President Obama to find all of the potentially hazardous objects in our solar system that could harm human populations and know what to do about it. And so we worked with our astronomers at the University of Hawaii. We built a telescope that could look at asteroids and comets that would be 2 months, maybe as much as a year out before impact. So kind of an early warning system. There's other astronomers that are looking at much deeper into space that can predict impacts much further out. But this would be to catch an early warning system. Well, why is that important? How many of you saw Don't Look Up? Hilarious movie. By the way, you don't pay for snacks in the White House. So, the fact is that there was a lot of artistic liberty taken in that movie. Like, astronomers don't figure out whether it's going to impact the Earth on a whiteboard in about 5 minutes. But they do figure it out. They do simulations, and they look at the trajectory of the object, and they determine how close it's going to come to Earth. And the interesting thing is, when these guys were working for me, they would come by and they would say, oh, this one has a 60% chance of hitting the Earth. And I'm like, what do we do? And they said, you wait, and then you take another measurement. And as you get more and more measurements, what happens? Your error goes down. You get a more and more accurate measurement. And so that probability of impacting the Earth goes way down to the point it was like 0.2. And so that's what we're really trying to do, is to track these objects. Well, this telescope is the one that, when Hawaii is in daylight, this telescope is in nighttime in Sutherland, Western Cape. So I came here in 2013 to propose the installation of this telescope. It just came online in January of this year. It took 9 years to produce the second copy of a telescope that was already operating in Hawaii. And people will wonder, like COVID, what that means. It would have just taken 7 years. I don't know why. But now, 2 to 3 times a night, the entire sky is covered looking for transits. That's moving objects that don't move with the rest of the stars. And those things are then cataloged by a global community of scientists that are interested in understanding whether or not there's potentially hazardous object. The last thing, I don't really have too much to say, except that a number of these missions have my fingerprints on them. And they orbit the Earth, taking data constantly. Data that we try and we share with the world, because we're trying to understand weather, we're trying to understand the way the oceans are changing, we're trying to understand global warming, and ultimately we're trying to understand climate change. And I don't care what your political leanings are, but the fact is, the Earth is getting warmer. And the fact is that, yes, it would have been on a cycle of warming anyway, but the existence of human beings has accelerated. And I know that may not be politically correct in some circles, but that's the fact. And there's not really anything we're going to do to change that, unless we figure out how to adapt. That's really what I think is the big challenge associated with climate change, is how will we adapt? Because some regions that are now wet will become arid. And some regions that are arid will now become wet. And that's going to change economies. It's going to make food scarce in different ways. And it's going to put countries at odds with each other, perhaps. So not only do we need scientists to try and understand the effects of this, we need diplomats to be able to begin to allow these changes to happen peacefully. Three commercial enterprises. Okay, so the thing that I'm most excited about space exploration is commercial enterprise. The commercial space sector is just opening wide up now. And in my mind, in fact, I just got done telling the CEO of SANSA that you don't need to partner with NASA anymore. Now you need to start talking about partnering with individual companies or maybe some billionaires if you want to make an impact in the space sector, space community. So there's this thing called CLPS, Commercial Lunar Payload Services. When we send humans to the moon, it will be after we've sent robotic payloads to the moon. That's in anticipation of sending humans, we need to understand the surface that they're going to. There's lots of other things. We want to try and get into permanently shadowed regions on the moon, which are some of the coldest spots in the entire solar system, where we think that most of the water that was originally on the moon, or went to the moon as the moon was forming, has now collected. So we'll send cargo, we'll send scientific instruments, we'll send rovers, we'll send robots to prep base camps for human beings, and it's just going to be a fantastic opportunity for anybody who wants to get into robotics and space exploration. The next thing that I think is just way cool is space tourism. We've got astronauts and actors now flying to space, and I think that's great because it means that someday it'll be like catching a flight from Johannesburg to Washington, D.C. I don't know that I'll ever be able to afford it, but it's still going to be, I believe it'll become commonplace. A little more affordable is this company called Worldview over here. And they are going to set up 7 sites, launch sites from around the world, one of which will be in Kenya, where several times a day, I think it's 8 people will climb into this capsule, 8 tourists, and it'll be like being in a lounge at your favorite bar. A balloon will lift you up into the ionosphere, and you get 6 to 8 hours of view of the horizon, what deep space looks like. You will also get the opportunity to look at the other balloons that were launched at the same time as you, and share that experience from one pod to the other. Then when the mission is over, 6 to 8 hours later, they'll cut the balloon away. You'll fall, and a parachute will open up, and you'll glide back down to Earth. They say landing gently. Who wants to be first? Oh, look ahead. The thing about governments being involved in space exploration is that when industry can't or won't do something, this is a purely capitalist point of view, when industry can't or won't do something, then the government should. And one of the things that we have just completed is 21 years of a permanently manned presence in space on the International Space Station. Well, the technology is now to the point that we can spin that off to industry. We can give it to entrepreneurs and businesses, and they can begin to building private space stations. some of which will be research labs that they hope to sell research time to governments as well as organizations, pharmaceutical companies, people preparing to understand what it's like, what's going to be like to venture deeper into space. Some others may actually be hotels in space. So you could go for a holiday in space if you want. You have to earn a lot of money first, I think. Let's talk about two new initiatives. Artemis and humans to Mars. So, what happens, by the way, is human spaceflight in the United States gets pushed around by whoever happens to be president at the time. And I've been around long enough to see one president say we're going to the moon, and the next president come back and say, nah, we're not going to do that, we're going to go to Mars. And then another president comes in and says, no, that's not right, we're going to the moon. And fortunately, the last president that we just elected, or elected a year ago, didn't change that agenda. So we're still going to the moon first. And so that program is called Artemis. And there have been 16 nations that have signed the Artemis Accords, which are a set of values by which these nations have agreed they will behave as we all go to the moon. Because we're not going to, no one nation should really be doing this alone. We're going to do this as a consortium of nations, pulling together all for similar sets of goals. And you can see, none of these is like, oh, France is going to supply the robots, or Canada is going to supply the mechanical arms, or NASA is going to supply the arms. These are values, which I think is really important as we move further and further out into space, and we come together as humanity to try and do that. We need to have common understanding of ways that we will behave. So that's what the Artemis Accords are all about. And as we go to the moon, there'll be these series of opportunities. There'll be cruise systems and airlocks. There'll be refueling flights. There'll be landers going to the moon, and there'll be ascent vehicles coming back up, and there'll be a gateway space station around the moon that ultimately will be used as the drop-off point for the start to Mars. And so you can see here, this was a strategy that was put together, I think, in 2015, but it's still valid. The Hubble Space Telescope has been taking images of our solar system. The International Space Station, we're learning how to live and work in a permanent way on the space station. The Orion and the moon, we're going to go to the moon, we'll explore that, we'll do that for some period of time while we develop the technology to do the really hard thing, which is send humans to the moon. Right now, it's so hard to send even robots to the moon that we don't believe it's safe to send humans to Mars. Did I say Mars? So at some point, and I don't have a time frame, we will send humans to Mars. And some of you will have children that will be scientists and engineers that work on the missions to Mars. So I think this is a fantastic time to be involved in space exploration. I know you're mostly aeronautics, but I really encourage you to think about space exploration and what you can do. There are plenty of ways to partner with organizations that are interested in exploring our universe and trying to understand our place in it. The really cool thing is you don't have to work for NASA anymore to be a rocket scientist. You can work for any number of organizations. In fact, there's a group at KZN that are working on rockets right now. And so it would be really cool to see South Africa launching their own rockets someday peacefully out into space. And I don't know how long it took, sir. But I want to say thank you to everybody for listening, and to the consulate in Johannesburg for sponsoring the lecture. And with that, if we bring the lights up. I have time for questions. I got one more. 41 minutes. It took 41 minutes to do that lecture. Oh, wow. That's longer than I thought. So, questions. And by the way, I've answered questions, everything, all the way from, is the Earth flat, to how the astronauts be in space. Anybody? Yes?
Do you ever worry that commercialization of space, that the focus will be more on capital gain rather than like science towards, you know, like human wellness?
You know, I don't. Because I believe that mankind is bigger than capitalism. But I think that it's going to be the capital drive that causes enterprise to move further out. Now, what I see is governments pushing forward. So we'll get started on the moon and we'll be followed very quickly by commercial enterprise. And same with Mars. Although Elon Musk says he's going to beat NASA to Mars. If he does, that's great. I just hope he does it safely. So, and I have a NASA lapel pin for really good questions, like that. Okay. Anybody else? Yeah, in the middle there.
So, judging from like the environmental conditions in space, you know, the temperatures and stuff, do you think that minerals we anticipate finding in other planets that may be useful for us in like Earth?
So I think your question, I can barely hear you. I think, and it's because I'm old, it's not you. I think your question is, do we think there are other kinds of minerals that we haven't discovered on Earth in space?
Yeah.
And the answer is, not that I've heard geologists talking about.
So couldn't we potentially like simulate the conditions there and anticipate the minerals we could potentially find on other planets?
Could we, something about
simulate the conditions on other planets and extrapolate that from what we have here on Earth?
Yes,
Try to find out.
we can, but it's really interesting. Simulating the conditions on Venus is really, really difficult. The pressure, the temperature, the atmospheric content. Simulating the moon even is hard. If we have a lab at Kennedy Space Center that is developing excavators and mining equipment for the moon. They need lots of what we call lunar simulant, which is the regolith on, or it simulates the regolith on the moon. But we're not sure we got it right. And so we need to go back, we need to get some more samples. We still have some rocks locked up, but we don't have a lot of the dust. Not a lot of it. Mars is totally the same sort of deal. We don't know for sure exactly what's there. Although we've sent some amazing instrumentation on the rovers, we just don't know it for sure. In fact, I have one colleague, when we sent a mission to roughly the northern latitudes of Mars to sample what we thought was water, her response was, well, you don't know if it's water until you taste it. And you just think about how hard it would be to design an instrument to tell you for certain it's water. You don't really know. That's a great question, and so you guys are going to have to hand these back. Straight back. Make sure he gets it. Okay, yes?
In your time working in the space industry, what is either a project or a moment that you're either really proud of or you look back at and think, wow, that was really cool?
Oh, goodness. So, I usually say I love all my children equally much. But for you, I'll pick two. landing the Curiosity rover on Mars. And I was going to show a video of what it takes to land on Mars, but it's no fun without the audio. So if you go, it's old, so you can probably find it on YouTube. If you go look up 7 Minutes of Terror, NASA, I'm sure you'll find it. And I don't know, how many of you have seen that? Yeah, you have. So it's a huge engineering feat to get from 17,000 miles per hour to 0 in 7 minutes. And when they do that, there's all of these configurations that the spacecraft goes through. It has to jettison the heat shield, it has to take radar pictures, it then slows down with a parachute, but not enough, and so then they cut the parachute loose and they drop the rover outside of the back shell, and they come down as far as they can on rockets, but they can't get too close because they'll build up a dust cloud, which will land on the instruments on the rover and ruin the mission. So then they hover and they lower it on a crane to the surface of Mars. It's just an amazing engineering feat. Nobody knew it was going to work. We tested it. We all had some degree of confidence, but nobody knew for sure that it was going to work. So that was one. And remind me that I was going to give you a second one, because I'm going to tell you a story now. When I first got my job in Planetary Science, I went out to the Jet Propulsion Lab, which is where they build the Mars rovers. And they were running a prototype of a Curiosity rover around an area that they call the Mars Yard. They were testing the wheels for traction and for the suspension to see how big a boulder it could climb over. Embossed in the tread of the wheel in reverse were the initials JPL. And I said, well, why do you have the tread laid out that way? And they said, well, it's a visual indicator so that every time you see JPL, you multiply by the circumference of the wheel and you know how far the rover's traveling. It's a cool idea. So I get on a plane, I go back to NASA headquarters, and I'm thinking about it, and I'm thinking, I don't want to leave JPL all over the surface of Mars. Why don't they change it to Earth or NASA or something else, you know? And so the guy who was working for me that was running the Mars program says, okay, we'll fix it. So they fixed it. They put in a series of holes in the wheel, which is cool. And the series of holes, which I didn't look at very carefully, would make an impression in the Martian soil, and you could look back and see how many of those you made, and get a rough idea of how far the rover had traveled. Because, you know, there's no GPS on Mars, right? So, just before launch, a fella came into my office, and he's waving this picture, and he said, do you know what this is? And I said, yeah, that's the rover wheel. And he said, that's right. And he said, you know what these are? And he points to the holes. And I said, yeah, those are the visual indicators so we know how far the rover had traveled. And he said, well, that may be, but it's also Morse code for JP. So they got, yeah, all right, one more and then I'll come to you, right? So the second mission that I just think blew my mind was the New Horizons mission to Pluto. We didn't know what to expect of Pluto. Most people thought it was going to be a dead rock. What we found was an icy world with ice mountains and ice volcanoes and tholins, which is a carbon compound that was being shared between Pluto and its moon sharing. We see tholins elsewhere in the solar system, but everybody thought it would be too cold out there to get these organic compounds. So yeah, and then there was this shot of Pluto, backlit by the sun, and you're looking through the atmosphere, the very tenuous atmosphere of Pluto, and it's like, it's almost like an emotional experience. So those would be the two, the Curiosity lander and the probe to Pluto. So, awesome question. Yes?
When we look at the mission for the mass sample collection, I hand over the mission to the cosmic physics. But in your opinion, you think that mission being successful without the element of humans in the collection of the samples in space?
Can we use those systems to successfully, I didn't make the stretch between Mars sample return and humans.
Now, like my question says, like for the mass sample collection or return, they are planning to use like the coding to do those things. Like it's an unmanned mission. So my question is, if you know, like when scientists or programmers they program something, they make a lot of assumptions, thousands of assumptions, and it would be millions of possible things that could go wrong that you give us.
Yes.
So do you think that the mission was successful without the presence of humans? Because if there's a million of things that could go wrong, then there's a million of
Yes.
humans.
There are millions of things that go wrong, and it is the human beings, the design engineers on Earth that think all those things through to try and determine what the risk is. Because every one of those events that could happen has a probability associated. And so it is the really smart human beings that think that through. That's one of the reasons I had confidence that the Curiosity rover was going to land, though I have to say, at the very last minute, I was quite nervous. So that's a great question. Can you pass that back to me? Yes?
I hope this is not a goofy question, but from the missions that you've been involved with, do you see humans finding life on other planets in the next?
How much time do we got? So, astrobiology, when I was running Planetary Science, used to report to me. And I have to tell you that there are, it's just, where do you even start? So, there's a region of space that nobody's ever been to called the Oort cloud. The Oort cloud is the furthest bit of the formation of the earliest formation of our solar system. Icy balls, just sort of so, in fact, they're so far out that they don't even orbit the sun, they kind of loiter in a sphere. So they don't make a belt, which most debris would. They're kind of in a sphere with billions of these objects. They're hard to image, but we know it's there because that's where comets come from. So every now and then, the gravity between the sun and Jupiter kind of line up on one of these objects, gives it a little tug, and then over hundreds of thousands of years, it comes screaming in towards the sun. As it gets closer and closer to the sun, it melts away the surface, and that cloud is what we call a coma of a comet. And as it leaves that cloud out into space, that's what we call a tail. So NASA, my division, flew a mission to a comet and flew through the coma of a comet, opened up a sample container, then brought it back to Earth. And we analyzed it with very strict protocols, I must add, to assure that we weren't contaminating the sample. And it was a good thing, because one of the things that we found in that sample, or those samples, I should say, were common amino acids. So now you ask yourself, what are amino acids doing in a region of space where no human being has ever been? Right? In fact, we redid the analysis on pristine samples just to be sure that we were measuring the real thing and not ourselves. And came back the same. So it's possible, once you start looking at where the water and the ice are around our solar system, Enceladus is spewing out water around Saturn. There's Europa at Jupiter, which is an ice moon with an ice shell that's a couple of kilometers thick, but inside it is liquid water that In fact, inside of it is 2 to 3 times more liquid water in it than the Earth has on it. We know it's liquid because we can detect the wobble in the orbit as Europa goes around Jupiter. On Mars, the Hubble Space Telescope has detected seasonal emissions of methane. Well, what makes methane? Cows. We haven't seen any cows on Mars. But life either excretes it or makes it when it decays, or geologic activity. We haven't seen either of those things yet on Mars. But this methane is emitted, and then the UV from the sun disassociates it, and then the next season it comes back. Well, where's that coming from? We don't know. So scientists operating the Curiosity rover have an instrument that's able to separate the isotopes of methane. And apparently, I'm told, that if you get a certain kind of ratio between certain isotopes, then you can be relatively confident that that methane came from geologic activity or it came from life. The problem is that the Curiosity rover hasn't gotten a big enough sniff of the methane yet to be able to do that sort of analysis. But it's entirely possible that there are microbes on Mars right now producing methane seasonally. So there's like just 3 spots in our solar system: Enceladus, Europa, Mars. But there's water all over our solar system. And wherever we find water on Earth, we find life. Is it possible that there's life beyond Earth in our own solar system? I say, yeah, there is. It's possible. If you talk to the astrophysicists and they take the cosmological model of the formation of our solar system, they will tell you that our star formed in a stellar nursery close to other stars. This is all simulation modeling, right? But at the dawn of our solar system, there were other stars close by. And those stars in that stellar nursery share the same Oort cloud material. So it's possible our neighbors have the same building blocks of life that we do. So you have to think that through. And what does it mean to us as a society if we find out that there is life now on Mars? Even if it's microbes. Does it matter? Is it just a curiosity? Or will it change our worldview? I don't know. But we should be thinking about that because it's coming. So that's a great question. And I don't know if I can reach you. Nope. So, yes, ID.
Sir, I wanted to ask you about the Atlas mission.
The telescope? Yeah.
So I wanted to know how accurate is the readings from the telescope, and also if there was to be, let's say, a life-threatening object from space that was to
I'm not getting what you're saying.
Oh, I was saying if there was to be a life-threatening object from space that was approaching Earth, are there any countermeasures to tackle that?
Oh, countermeasures to deal with the inbound.
To deal with impending threat from space or anything.
Right. Yeah. So, NASA, Europe, Japan, and others have found and cataloged what we believe is 98% of the planet killers, besides asteroids that might have killed off the dinosaurs. Right? We're constantly finding more and more. Most of them fly right by us with no problem. There are some that just about every week are flying between us and the moon. That's how close they get. But they're small. And so if they come inbound, there was a lot, let's see, it was in 2008, I think, maybe it was a little later than that, there was a smallish asteroid that became a meteor, ultimately became a meteorite, that came in over Chelyabinsk, Russia. And it lit up the sky, the morning skies. People were at work and going to work. People rushed to the windows to see what this bright light was. And that's when the sonic boom, pressure wave, hit the glass of the office buildings. And that's how people got hurt. Thankfully, nobody died, but lots of people with cuts and abrasions because the glass blew out when this meteor came in. So there's, now I'm telling you this why. So there's a group formed by the United Nations that advises the United Nations Committee on Peaceful Uses of Outer Space that is specifically looking at what to do if we find one that's inbound. And they have protocols. If we find one that's up to a certain size, then most likely it's just going to burn up in the atmosphere. Beyond that, up to another size, and I used to have a chart, but I don't have it handy. I don't have the dimensions memorized. Up to another size, it's basically just going to do what happened in Chelyabinsk. Beyond that size, I think it's 114 meters across. We've cataloged a very high percentage of them, so we know whether or not they're coming through. Like I said before, once we see any that we think are suspect, we just keep watching them, because then the error associated with the prediction of their trajectory goes down. And as we do that, then usually they miss us. So I tell people that they don't have to lose sleep tonight. But if there was some big one coming in, there is a group within the United Nations that's talking about how we might mount a mission to either move it out of the way if we've got enough time, or perhaps break it up and try and encourage or give it a little nudge to try and get it to just raise by. So that's a great question. And one I don't get very often. So, okay, who's going to pass this back? All right. So, are we almost out of time? We are out of time. This is the last one. Last question. Right.
I think a lot of people here are quite interested in this field, but I think it can be quite intimidating when you move from. There are a lot of people here doing aeronautical or maybe mechanical, and they don't really know what to do after varsity. If they need to do their masters, if they need to go to a specific company. So, like yourself, you went from physics to electrical engineering. Was there a reason for that? Is there something that people in undergrad or even postgraduate focus on and kind of get to that point?
So, it's a great question. When I get that question from learners, they say, what should I study? And we're talking about grade 7 and 8. I say algebra. They don't like that. There's no secret code to having a career like mine. And let me just tell you, I know we're out of time, but let me just tell you my story. Right? In the mid-70s, I was in college studying physics, that's true. And we had an electronics laboratory where we were playing with these things called microchips. They were kind of new. And in fact, there was one physics professor who said they're just a fad. But they interested me, and I built a few circuits to track a ham radio satellite as it went overhead. We did a thing where we, where the Lissajous figure is. beamed a laser across to the Student Union building and we made figure eights and that sort of thing. So it was cool. And then I was going to graduate. I had to figure out what am I going to do next. And down the road from where I went to college was a company that made cash registers. Back in those days, cash registers were mechanical things. You push a button, the numbers would pop up, and then the drawer would open, and the cashier would have to count out change to you. Today, you just tap your card, right? And I saw that coming, and I said, these things are going to become electronic, and I want to work on cash registers. Well, the cash register company saw the same thing, and they were hiring people to work on making their cash registers electronic, but they weren't hiring physics majors. They were hiring electrical engineers. So I didn't get the job in cash registers, and I had to go with my second choice, which was aerospace. I will tell you, what I did was I ended up working for General Electric Company as a radiation physicist, and over time moved from physics to systems engineering. And then it became clear that what would help me the most in my career was to go back. So I didn't go straight to master's. I got some experience, and then I went back and I got a degree in electrical engineering. That's my path. But there are dozens of other example paths for successful people. And I would say, what do you do well? And then follow that, right? People say, what's your passion? I think that's antiquated. I would say, what is it that you're good at? And then just capitalize on it. So, that's a great question. Thank you very much for listening. I think it's been a pleasure. In 15 trips to South Africa, hundreds of lectures. I've never been to Wits before, and you guys have been a great audience. Thank you so much.
Thank you so much for that amazing presentation. It was also really, really inspirational, and both you guys are something wonderful.
Thank you. Thank you very much.